Welcome to lecture 5.2, degrees of unsaturation. This is going to be a strategy that's going to make the drawing of constitutional isomers a whole lot easier. Even as we have small molecules and get to much larger molecules, this strategy is going to make the drawing of constitutional isomers a whole lot easier. So if you are worried about it, don't worry. You'll be well equipped by the end of this lesson. So I want you to view degrees of unsaturation like an accounting system for hydrogen. And what I mean by that is, let's say I ask you for the constitutional isomers of this molecule, C3H8O. Drawing molecules that have 3 carbons and an oxygen isn't too difficult. Unless you make a erroneous mistake and add an extra carbon, usually it's pretty easy to make sure you have 1 oxygen and 3 carbons. The hard thing is that in organic chemistry, we don't tend to draw in the hydrogens. So if you want to guess and check through structures, you're going to have to draw in all those hydrogens, make sure you make no mistakes and count them, and that's going to take a lot of time. So what DOU is going to allow you to do is only worry about the carbons and oxygens and these bigger atoms. DOU is going to entirely trivialize the hydrogens. If you handle your DOU correctly, you'll know that your hydrogens are correct as well. So what is a DOU in the first place? Well, we're going to use this system to account for all the hydrogens. So essentially, the DOU is going to be a proxy measurement for hydrogen. And to understand that, let's look at this 2-carbon molecule here. Now, right now, we have no double bonds, which means that this molecule has 6 hydrogens. I'll draw them in here. Now, if we add 1 pi bond, that doesn't come free. You'll notice that we actually have removed 2 hydrogens in the process, 1 on each carbon to make room for that double bond. So yes, we did add a pi bond, but that came at the cost of 2 hydrogens. The same is true if we go from the double bond to a triple bond. The addition of an extra pi bond takes away, once again, another hydrogen. So once again, a pi bond costs 2 hydrogen. And if we started from the single bond, we could imagine that 2 pi bonds costs 4 hydrogens. So that's excellent. We have this idea that a pi bond is kind of worth 2 hydrogens. Something else to consider is rings. So let's say we have a 3-carbon compound here. If we look at this, I'll write down rings here. If we look at this molecule, this propane, we'll see that we have 3 hydrogens here, 3 there, and 2 there, for a total of 8. 8 hydrogens. Now, instead of adding a pi bond, let's just close the ring. So let's make a bond between the first and the last carbon. Right, we're not adding any extra carbons here, but you'll notice that we do have less hydrogen. Again, to make room for that extra bond, we had to get rid of 2 hydrogen. So now that we have 6 hydrogens, that means that 1 ring, which I'll represent with a circle, 1 ring also has a cost of 2 hydrogens associated with it. So considering this, here's how I want you to understand DOU. Here's your legend for DOU. A double bond, or 1 pi bond, maybe I'll say that more specifically, 1 pi bond is equal to 1 DOU. Of course, if you have 2 pi bonds, that's going to be 2 DOUs. And every time that you close a ring, 1 ring is also going to be equal to 1 DOU. And you're going to add all of these up across your molecule. So let's take a quick sample of this and take this big molecule here, drawn below. Now, from a drawn structure, you're able to count the number of pi bonds and the number of rings. So by doing this, you should be able to calculate the total amount of DOU. Now remember that each time we have a pi bond or a ring, that costs 2 hydrogens. So another way you can view this is that 1 DOU is equal to the loss of 2 hydrogens. So let's take a look at this molecule. Here, I'm going to highlight the pi bonds in red. We can see that this aromatic benzene ring has 3 pi bonds. We also have a pi bond between this carbon and oxygen. There's also a pi bond here, which is the alkene. And note that we have 2 pi bonds here in this triple bond. Now in total, that gives us 1, 2, 3, 4, 5, 6, 7 pi bonds. And we also need to account for the rings. Now the only ring that's in this molecule is found here. So for every ring as well, we're going to include one ring. Now that gives us a total of 8 units, or 8 DOU, which based on this rule means that we've lost 16 hydrogen. So great. If a molecule is drawn, you're able to look and calculate the DOU of the molecule. But how are we going to use that for constitutional isomers? Well, first, let's understand how we can get the DOU from a molecular formula. Now, 2C plus 2 is an equation that may be familiar. This has to do with saturated carbon. And here we're saying saturated in terms of no double bonds. It's fully saturated with hydrogen. So 2C plus 2 for any equation gives you the number of hydrogens that would fully saturate the molecule. So for example, and the number of hydrogens. Let's say we took a molecule with 2 carbons. Well, 2 times 2 plus 2 gives us 6. And indeed, for this molecule, we have 6 hydrogens. If I was to add, let's say, another 2 carbons, I would change this number to 4, and this then becomes 10. 2 times 4 plus 2. And you can see that the saturated carbon chain has 10 hydrogens. So great. How are we going to use this to our advantage? Well, the DOU can also be calculated directly from the molecular formula using this equation. 2C plus 2, which again represents the number of hydrogens that you would have if there was no double bonds and no rings. Then you're going to take this and you're going to subtract the number of hydrogens from it. You're also going to do a couple other things. Now, these are less common. Usually you'll just be dealing with this. But in case your molecule has nitrogens or halogens, you're going to subtract the number of halogens. So this represents chlorines or bromines or fluorines in your molecule. And you're going to add the number of nitrogens. Again, these are usually less common, but do be aware of them, and we'll cover an example with them below. Now, if you take this whole added up sum and you divide it by 2, this is going to give you your DOU. Now, this is an equation that I would recommend memorizing, unless it's provided to you on an assessment, on a test, because it's very, very useful for things like this. So, how is it so useful? Well, let's quickly think about what we learned about DOU above. If a molecule, for example, has 2 DOU, that means that that molecule must have at least 2 double bonds, or a double bond and a ring, or a triple bond. One of these situations must be true, because we know that the molecule from its formula is missing 4 hydrogens. That's why it has a DOU of 2. So here we have 2 pi bonds. Here we have a pi bond and a ring, and a triple bond also has 2 pi bonds. And so the really cool thing here is, as long as you have a good understanding of what the DOU of your molecule is, and you make sure the number of carbons, oxygens, and nitrogens and atoms like that are correct, if the DOU is correct as well, that means the number of hydrogens is going to be guaranteed to be correct, which is awesome. So let's do a couple examples of calculating this DOU value. We'll start with C3H8 oxygen, with 1 oxygen. So here, we'll take 2 times the number of carbon plus 2. We'll subtract the number of hydrogens here, which is 8. And since we have no halogens or nitrogens, we get to ignore those terms. We divide this value by 2. So this gives us 6 plus 2, which is 8, and 8 minus 8 is 0. And this is also a very useful thing. 0 DOU tells you that this molecule is not allowed to have any double bonds. It has no pi bonds. And it can't have any rings either. So when it comes to drawing constitutional isomers, all you have to do is make sure that your molecule has 3 carbons, 1 oxygen, and no pi bonds or any rings. And the number of hydrogens is guaranteed to be correct. Now let's look at a bit bigger of a molecule, a bit harder of an example. We'll look here at CH, or C8H15NO2. So, same thing, 2 times 8 plus 2. Subtract 15 from this. And importantly, we don't include the oxygens. The oxygens don't show up in the term, but we do need to include the nitrogen and add a 1 here. If we take this and divide it by 2, we're going to get 16 there, plus 2 is 18, minus 15 is 3, plus 1 is 4, and 4 divided by 2 is 2. So 2 DOU. Now, here's what would happen if you forgot to include the nitrogen. Just an important learning lesson here. The number you would get would actually be not a whole number. You would have 1.5 or 2.5 or some decimal. If you ever get a decimal, you've made a mistake. The DOU is always going to be a whole number. So pay attention to that. If you do catch a decimal, don't try to figure out what a half bond is. So make sure you include the nitrogens in this case. As we mentioned above, 2 DOU could be any one of these situations: 2 double bonds, a double bond or a ring, or a triple bond. So as long as the molecule that you draw has 8 carbons, 1 nitrogen, and 2 oxygens, and 2 DOU, you're good to go. Now, I'll prove that with an example here. Let's just draw a straight chain of 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. I'll put a nitrogen on there somewhere, and I'll put 2 oxygens on there. So now this molecule, as drawn, without any hydrogens, has 8 carbons, 2 oxygens, and a nitrogen. Now let's quickly add in the 2 DOU. So I'll add these 2 DOUs as double bonds to my oxygen. That means that this is going to be an aldehyde with a hydrogen here. And this nitrogen is going to have to be singly bonded, as we don't have any degrees of unsaturation left. So it's going to have to be connected to 2 hydrogens. Again, the reason that's true is because this is a neutral molecule. There's no charge presented here, which means we can't just suddenly produce a charge here. So now that I've done this, well, turns out I can assure you that we have 15 hydrogens. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And look at that. Now, to draw other constitutional isomers, you could simply move this carbonyl somewhere else. Or you could replace this double bond with a double bond here. There really are tons of possibilities when it comes to picking your constitutional isomers. Now, earlier in section 5.1, I provided this example, and I said, I asked you to draw 3 constitutional isomers. Let's see how we can do that much more quick with this tool. So let's quickly plug this into the equation. 2 times 10 plus 2 minus 18. That's going to give us 22 minus 18 is 4, and 4 divided by 2, once again, a DOU of 2. So let's do one example that's a straight chain of 10 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do one example that has 2 rings. After all, we have room for 2 rings in our molecule. So for example, here's a molecule with 6 carbons in a ring, and we can put another ring here, like a square. Now, that is only 1, 2, 3, 4, 5, 6, 7, 8 carbons, so let's add some extra carbons to make that 10. Right, quite a weird-looking molecule. And for the last one, let's do a molecule with 1 ring and 1 double bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 with a double bond. So all of these molecules, quickly let's just add 2 double bonds here now. So all of the molecules drawn represent 10 carbons, and they include the 2 DOU. So now all I need to do is throw on 3 oxygens somewhere. Remember that we can't make them double bonded since we don't have any more DOU available. And really, you can put these OHs anywhere you want as long as it's a legal position. You're not violating the octet rule. And there we go. I'll only count one of these, but if you want to, take the time, draw the hydrogens in, and notice that they are all going to have exactly 18 hydrogens. For the top one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And just like that, we don't have to worry about counting hydrogens anymore, and we don't have to use guess and check when drawing constitutional isomers. So hopefully that helps with your constitutional isomer woes. And now we'll move on to different types of isomerism, starting with the introduction of the Newman projection. I'll see you there.